Hello everyone. The principles of classical physics appear to break down at the quantum level. We are told that many physical realities take place at the same time, single quanta have multiple states, entangled particles display spooky action at a distance, and so on. This is not the first anomaly in the history of science. For a very long time, many cosmic phenomena seemed equally hard to understand. For example, planets move forward and backward across the sky, pendulums precess over time, stars appear to swing, and so on. Pre-modern philosophers could not explain these phenomena with simple concepts because they assumed that cosmic spheres were spinning around a stationary human world. When this assumption was given up, consistent explanations became possible. The lesson of this example is that something similar could be going on in quantum mechanics. If everything looks strange, then maybe something is wrong with our starting assumptions. The goal of our presentation is to suggest that quantum phenomena are not intrinsically non-classical. They just happen to be misunderstood because of the assumption that classical wave interference is an illusion. When we look at the Sun, it is tempting to assume it really travels around the Earth. Similarly, when two waves intersect, it is tempting to assume they go through each other unperturbed. This wave appears identical to this one and therefore has nothing to do with this one. As it turns out, this assumption is problematic. Let us consider the case of two pulses that propagate in opposite directions. At first they travel towards each other, then they overlap for a brief instant, and finally they seem to be going away from each other. As far as we can tell, the waves propagate through each other, as if they never met. Still, in the region of overlap, we can only detect a single wave whose amplitude is equal to the sum of the two component amplitude vectors. This is easier to see in the case of co-propagating waves. If the two component vectors are equal and point in the same direction, the net amplitude is twice as high. If they point in opposite directions, the net amplitude is zero. In short, the nature of interference is captured with precision by the operation of vector superposition. Vector summation is a common operation in classical physics. It works for any directional process. For example, if this soccer ball was hit only by the white player, it would have gone in this direction. If it was hit only by the red player, it would have gone in this direction. As it happens, both players hit the ball at the same time. The net force acts on the ball in this direction. Therefore, we expect the ball to move accordingly. In both cases, we have component vectors and net vectors. Yet there is an important difference. In the case of discrete objects, we describe the net state as physically real and the component vectors as virtual. In the case of waves, we describe the component amplitude vectors as real and the net state as an illusion. Note that the two approaches are quantitatively equivalent. It makes no difference from a mathematical point of view which interpretation is chosen. A plus B and C are interchangeable in any equation, and either one of them could be real. The problem is that we have to change our interpretation of output waves if we change our interpretation of superposition. If we assume that wave interference is real, then we must also assume that there is only one big wave in the area of overlap. If so, then we can no longer claim that this wave is the same as this wave. They look identical, but their source of energy is uncertain. The standard interpretation of amplitude superposition is that waves go through each other, and that interference fringes are just a measurement artifact. You might think this is based on solid evidence. Unfortunately, this is not so, for two reasons. First of all, it is not possible to prove that waves go through each other at every point. For example, consider the intersection of two optical beams. If we isolate a single bright fringe with a narrow slit, the output projection does not separate into component beams. On the other hand, if we open up several bright fringes at the same time, the net projection will separate in two, even if the dark fringes are blocked with small obstacles. Secondly, it is not possible to observe the existence of two beams in the area of overlap. Instead, we always have the appearance of a single beam with a specific pattern of amplitude modulation in cross-section. Moreover, if we take a single beam and modulate it with a special filter, we can reproduce the same exact state that can be observed during two-beam superposition. If this output state is identical to this net state, then it will actually evolve in the same way. In short, the two interpretations of superposition are not just mathematically equivalent, they also entail identical physical implications. In the previous example, we used unmarked beams. Perhaps this is the reason for confusion between the models. What if we used polarized beams in order to tell them apart during superposition? For example, we can take the projection of two beams with equal frequency and orthogonal states of polarization. For simplicity, we can use a narrow slit to isolate a small section of the projection where the two beams are in phase. Let us analyze the output beam with a diagonal polarizing beam splitter. If we block the lower beam, the upper beam is split 50-50 because it is polarized in the vertical plane. If we block the upper beam, the lower one is also split 50-50 because it is horizontally polarized. What happens if both beams are open at the same time? The immediate observation is that all the radiation is transmitted and nothing is reflected. If we assume that light waves do not interact, we must also believe that each beam is split 50-50 as before. It just so happens that we have two components that are out of phase in this channel. Opposite equal vectors cancel out and the net state is 0. In this channel, we have two components that are in phase. Parallel vectors add up constructively and we get a net increase in observable energy. In short, the observed energy redistribution can be described as an illusion. The superposition of vertical and horizontal amplitude vectors in phase produces a diagonal net state of polarization. If we assume that interference is an illusion, then we have to believe that the net state is not real. The two component states are real. However, if we take a single beam that is diagonally polarized, it will pass through the diagonal polarizer in the same way. Any measurement that we can do on this state is going to produce the same results as this state. So if we assume that the net state is real here, we get the same observations. It may seem that polarization is not the best marker for our purpose. What if we focused on frequency instead? Suppose that we have two stable monochromatic beams with a small difference in frequency. For clarity, they are represented in this drawing by different colors. The most obvious feature is the appearance that the beams go through each other unperturbed. This is a red beam, and this appears to be exactly the same beam. Why should anyone think it is not? The problem is that we cannot observe the input frequencies here, where the two beams are superposed. Instead, we see what looks like a single beam at the average frequency. The only peculiarity is that this net frequency has a specific pattern of amplitude modulation in the cross-section. What if we now take a beam at the same carrier frequency and use a special filter to modulate the amplitude at every point of interest? If we do it right, we can recreate exactly the same state that happens during the superposition of two beams. This is where things become interesting. If we allow this state to evolve as it propagates to the right, it is going to split into two beams with the same properties as the beams that we observe here. Consequently, we can assume that the beams go through each other unperturbed, in which case interference is an illusion, or we can assume that interference is real, in which case the identity between input and output beams is an illusion. The two interpretations are equivalent in theory as well as in experiment. When we move on to the level of quantum phenomena, this equivalence is lost. For example, if we assume that interference is real, we expect to see fringes here at the classical level as well as at the quantum level. After overlap, we expect the net state to evolve into two groups of detection events, knowing that the origin of each quantum is no longer accessible. In contrast, if we assume that interference is an illusion, then we must also assume that quanta go through each other unperturbed. Therefore, they cannot bunch into fringes in the interference volume. We expect to have fringes at the classical level, but not at the quantum level. As it is well known, quantum detectors reveal fringe distributions, just like classical detectors. Therefore, we cannot satisfy the interpretation of non-interference and the observations with a single story. We need to invent new physics. For example, we could assume that interference only happens when we look at it. Some types of measurements cannot be done at the same time. We can express this as a principle of complementarity in order to suggest that physical reality changes on the basis of our experimental choices. As long as we believe that interference is an illusion, we have no choice but to believe that classical analysis breaks down at the quantum level. Another reason for concern comes from the interpretation of net states, where we have to decide which vector is real. For example, let us consider the superposition of two polarized beams which happen to be in phase. If one polarization is vertical and the other is horizontal, the mixed beam is going to be polarized in the net state, which is diagonal. What happens at the quantum level? If we assume that interference is real, then we believe that the net diagonal state is also real. We start with two populations of photons, vertical and horizontal, but we end up with a single population in which all the photons have switched to the diagonal state. Please note, every single photon is in the net state and it is well defined like any classical entity. In contrast, if we assume that interference is an illusion, then the net state of the classical beam is also an illusion. We expect the photons to remain unchanged in their starting vertical and horizontal states of polarization. Therefore, we have a problem. How can we expect vertical or horizontal photons to behave as if they were in the net diagonal state? At the classical level, we say that the beam is in two states at the same time. In the same spirit, we end up describing each single quantum as if it was in two Schrödinger cat states at the same time. Obviously, it sounds strange to claim that a single entity can move in several directions at the same time. This kind of behavior is never observed in actual experiments. If we believe that interference is not real, we are forced to assume that quanta can be undefined when we cannot see them and instantly collapse into well-defined states when we can. A similar problem can be found in the analysis of entanglement. Consider a source of identical photons that are emitted in pairs in opposite directions. Every photon in this beam has an identical partner in this beam, but the photons in the same beam have different states. The quanta from each beam overlap and therefore display the appearance of local interference. We have to decide, is this interaction real or just an illusion? If we assume that interference is real, then we have to believe that the state of each photon changes during propagation. This means that we start with vertical and horizontal photons, but end up with diagonal photons. All the photons are now in the same net state. So if we measure the correlation of detection events, we expect to observe violations of Bell's inequality because the measured quanta are not in the same state as the emitted quanta. What happens if we assume that interference is an illusion? The net state is going to be the same if we observe the beam as a whole. Still, we assume that individual quanta are not affected in any way. Therefore, we expect this property to be revealed in quantum measurements. Individual quanta should only produce coincidence events that obey the limit of Bell's inequality. Yet this expectation is contradicted by experimental observations. If we persist that interference is an illusion, we have to invent new physics. For example, we might suppose that photons have non-local properties and that measurements at one end can influence the outcome in the other. In short, the principles of classical mechanics do not fail at the quantum level. It is only the assumption of non-interference that breaks down. To sum up, the sun appears to travel across the sky every day. If we take this experience for granted, we get the appearance of anomaly in celestial mechanics. Likewise, it may appear that waves do not interact with each other. If we take this observation for granted, we end up with strange interpretations in quantum mechanics. In both cases, the solution is the same.